Okay, let's get started. Hello everyone and welcome to Ethproofs call number 7 dedicated to EVM guests. We have about 70 people on the call and people are trickling in. Let me quickly share my screen. Up. Okay, so as usual, we have a Telegram group. There's about 500 people in the group now. There's some good conversations. If you'd like to join, just scan the QR code or join with the link below. Of course, probably most of you watching this video knows about this. In order to have a zkEVM, we need two things. One is we need an EVM implementation, which we call the Geth program, and we're going to compile that to a zkEVM. And in 2025, we made a huge amount of progress on zkVMs, their performance and the diversity. I feel like there's more work to be done on the Geth. We've mostly been, to a large extent, relying on revm, and we need more diversity there. So in 2026, we're going to have two call series. So in addition to the Ethproof call series, we're going to have a new ACD breakout called the L1 zkEVM ACD breakout. It's going to be led by Kev. It's going to happen possibly monthly, possibly bi-weekly. I guess Kev will tell us all about it. And it's kicking off very soon, in a couple of weeks, on the Wednesday, February the 11th. But yeah, going back to the Ethproofs call series, we're going to be focused in 2026 on security. So in addition to the guests, we're going to be discussing Poseidon 2 on March 20th. I'll be sending out the poll for the calendar invites shortly after this call. We're going to be talking in particular about the Poseidon prize that was announced on Twitter recently. That's a $1 million prize. And then there's going to be all sorts of other miscellaneous security topics scheduled for this year, including formal verification. Now, in order to kind of introduce this new topic of guests, Fara has created this new guest tab. So right now on Ethproofs, we have 4 different guests. And as you can see, that of the 12 provers, 10 of them are using revm, and we're kind of slowly building up the diversity. And what I'm expecting will happen over the course of 2026 is that this tab will really blossom and expand significantly. Now, one reason for having this call is that there are some EL clients that are written in zk unfriendly languages like Java, and so really there's kind of 2 options available. You can either rewrite your state transition function, or you could adopt an existing one as your Geth program. And it seems like potentially Besu will go down the rewriting path. Potentially Erigon is going down the adoption path with EVN1 and Zilkworm. And there's still potentially a final decision that needs to be made for Geth. But yeah, all of these entities will be speaking today. Now, in addition to the Geth tab, we now have a new spreadsheet called the Geth tracker, which basically tracks all of the EVM implementations that I could find. I found about 40 of them, and basically try to bubble up those that are most suitable to be used as Geth programs. So, in addition to all of the implementations that come from the Ethereum ecosystem, whether it's the L1 or the L2 ecosystem, we also have some implementations from other L1s, for example, Monad, Polkadot, Falcon, and Near. And maybe some of these implementations, which are securing, sometimes billions of dollars today and have existed for several years, could be basically adopted as Geth programs. And so we'll hear from some of the maintainers of these EVM implementations. So today's going to be an extremely busy call. We might overflow and overrun beyond the 2 hours that is slotted. We have 14 presentations, each 5 minutes. So we're going to have first the EL teams present what their plans are and what EVM guests they've tentatively adopted so far, and then we're going to be talking about other candidate guest EVMs, most of which are kind of outside of the Ethereum ecosystem, and then we're going to have a closing talk on Zero OS. But before these 14 presentations, we have 10 quick updates, as usual, 2 minutes each with some Q&A. And yeah, without further ado, I'd like to invite Mo to talk about Pico and achieving real-time proving on 16 GPUs.
Hi, Justin. This is Alan. I will be presenting the recent updates on the Pico Prism.
Perfect.
All right. Yeah, let's see. Can you all see the screen?
Yep.
All right, cool. Yeah, so I'm going to present some of our recent updates on Pico and some intermediate updates here. And then 3 months ago, we were releasing this first version of a Pico Prism that was deployed on 64 GPUs, where we employed this divide and conquer method to use sub-blocks to run the whole block workload. So basically, each block is divided into 7 sub-blocks and approved on 7 GPU machines, each with 8 GPUs in total. And then they were all aggregated on the eighth GPU machine. So with this divide and conquer, we were able to achieve almost the real-time proving. We were able to prove the more than 99% of the Ethereum blocks under 12 seconds for all the blocks in total, like 7,200 blocks executed on September 1st, 2025. And since then, we have been developing many different updates as well as optimizations for the current architecture, because obviously 64 is very far from the 16 GPUs. So there are different optimizations that we have been employing. For example, we have this updated AOT compilation compared to what we originally have, which was interpreter-based emulator. So the ahead of time emulator is replacing our original interpreter-based emulator with native compiled Rust code generated directly from ELF library. We just remove those pre-instruction decode and dispatch overhead during our original emulation. So the emulation whole procedure will be able to be accelerated up to. So this is one of the biggest progress that we have. And then there are still many different optimizations that we haven't applied, but yeah, it's ongoing. There's also
Okay,
data
fantastic.
locality. Yeah. Yeah. So final result is like this. We still have like many things going on, but we are now able to prove the more than 99% of the time under 12 seconds for exactly the same set of blocks now. So yeah, so this is the intermediate, and we hope to see that we were able to prove all the blocks, recent blocks within 12 seconds or even less than 10 seconds real soon. Yep, that's all.
Okay, perfect. Just as a heads up, I'll be keeping strict timekeeping because we have a very packed schedule. Congratulations, Alan, and it's good to see the AOT optimization being implemented everywhere. And great to hear that you have more optimizations coming. That's great news, of course. Next up, we have E from Axiom.
Hey everyone. So yeah, I'm here to present OpenVM 2.0, our recent release, which proves Ethereum in real time on 16 GPUs. We've updated OpenVM to now have 100 bits of provable security and a proof size of under 300 kilobytes. Onto the numbers. On a string of recent mainnet blocks starting from block 24 million, you can see the histogram of proving times on the bottom left. We got a P99 proving time of 11.8 and an average of 6.7 seconds on a cluster of 16 5090s. And we also introduced a new benchmark, which is to actually assess the proving performance of OpenVM on a benchmark called CoreMark, which is typically used for embedded CPUs. And so we looked at the scaling of the proving speed as the number of GPUs increases. And we're able to go from 11.4 megahertz on one 5090 all the way up to 139 megahertz on the full cluster. And finally, like Alan was saying, we also implemented AOT execution, and we're able to execute RISC-V at 3.8 gigahertz. So all of this is powered by a new multilinear proof system backend that we've implemented for OpenVM that's called Swirl. So it's based on WIR and has particularly fast recursion. So you can check out the details on the OpenVM website, and we just posted a more detailed release blog yesterday. Happy to leave a few seconds for questions.
Perfect. That was super quick. I guess one question is, okay, there is a question from Clément already. Do you have an idea why the histogram of latency peaks has a second mode around 11 seconds?
We're actually very curious about this as well. We're not totally sure. One hypothesis is that I think Aztec has been posting a lot of blocks which use very heavy elliptic curve precompiles. And our guess is that these are the blocks that contain those operations, but we're not 100% sure.
Cool. And I guess similar to Alan, do you feel like there's more optimizations to come, or are we starting to reach saturation in optimizations?
No, I think there's quite a bit of things on our roadmap. So yeah, hopefully we can deliver some more improvements in the coming weeks.
Perfect. Congratulations. Next up, we have Jun, who will talk about Prism zk attesting.
Hi, it's Jun. So I recently worked on the optional proofs with aka EIP 8025. So I'll prepare a 1 minute demo video, and before that I'm gonna just briefly introduce about how this local network works. So it consists of 8 nodes, and there are 2 stateless nodes here, which means it doesn't have EL at all. So there's an external prover right here to submit execution proof when it receives the block gossip events from the network, so that these 2 nodes can follow the chain and attest to the chain so that it can participate to the consensus as well. So yeah, let's see a quick demo here. So in the left side, I'm running a kurtosis, and in the right side, I'm running a dummy prover here. So yeah, I'm gonna skip some very boring steps. And yeah, there are 2 terminal sessions following the load here. So the first one is the stateless node that receives a proof from the prover, and the right side is the stateless nodes that receives proof from the gossip sub. So if you want to see in Prism that if your node follows the chain well, you can see this kind of log, sync new block, sync new payload. And you can see those 2 logs are appeared repeatedly in both of the sessions. So it means that it can follow the chain at all. And maybe I can forward here. If we see Dora, let's see, there are some attestations happening. So there are no validators. There are all validators participating in the consensus. So which means it can follow the consensus without the EL, only relying on the external prover and verifying itself. So that's it from my side.
Very nice. Do you know when you'll have a mainnet validator running this?
I'm not so sure. So there is still an ongoing discussion about the overall architecture about the EIP 8025. So I think yeah, this is just exploring some feasibility. So I guess we are targeting the G fork, but yeah, we have to discuss more.
Okay, perfect. And I also look forward to potentially using it on my validator. I see we have a question for Eon in the chat from Sergey. Do you know if Scroll L2 plans to upgrade to OpenVM 2.0?
Yeah, obviously the final decision would be up to Scroll's governance, but yeah, that's the plan.
Okay, perfect. Next up, we have Tamir, who will talk about SP on Hypercube being released potentially.
Hi, everyone. I wanted to announce the open source of Hypercube. And so we released our version 6.0.0 beta, which is the beta release of Hypercube to crates. And also it is available on GitHub. And one new thing about it is the GPU code is also under our MIT Apache 2 license. The audits have been completed, and we will have a mainnet release very soon. But you can try it out and let us know all the things you find. And in the future, we'll also have improvements to proof size as really more bottlenecked by audits at this point, and more to come.
Wow, absolutely amazing. Kev is asking, what was the reason for going full MIT Apache?
Yeah, I think we realized that this is like something that is important for the community and for like resilience as it will be used for L1 proofs. I think that everything is really just about we're still trying to find a balance of like the business and the public good kind of place here. So currently our business model is like proving a lot of L2s and our collaborations with those ecosystems.
Very nice. On the slide that I'm showing here, we have basically some updates highlighted in yellow. So we have now OpenVM and Pico that can do 10 kilowatt proving, and we have SP1, which is now dual licensed. And we also have some improvements on the proximity gaps and the provability. So this table is very, very quickly becoming all green, which is absolutely amazing. Next up, we have Clément Walter, who will talk about Stark 5.
Yes, I'm here. How do we share the screen with, I'm lost, with Zoom?
There's a green button in the bottom with share.
Yeah. Got it, all screen. Authorizing. Oh, I so much never use Zoom. Do you see the screen or not yet?
We can see your calendar. So if you unshare, okay, that's better.
Yeah. Anyway, so yeah, this is a quick presentation about this project that we made during the past 3 days with Antoine. So we built a RISC-V prover with Starkware tech. So we were very close to, of course, everything Starkware has built, but as you know, Starkware is focused on their own stuff with Cairo and Starknet. So we said, okay, why not building a RISC-V prover based on the experience that we had? So it's more of an engineering perspective of a recent build of a RISC-V prover. I asked GPT to generate this ugly image just to have something a bit nicer because I drew the slide really in 15 minutes later on today because Antoine was off. So the tagline is really a new agent native RISC-V RV32IM prover because we did this like a month ago and it has been 99.9% AI code written. Does not mean that we have not read the code. It means that we have been really by design from the very beginning been working with the fact that the AI will write the code and we will be focusing instead of the spec and we will leverage the agent to do the things that usually humans don't want to do to make sure that we can sort of have something that is both auditable more easily and smoother. So my first slide was like, okay, the team. So Antoine is not here and I. Just to be clear, this is not a Kakarot project. Kakarot does not exist anymore. It has been sold to Zama. This is not a Starkware project. This is so don't go to Starkware. People has something. Don't think about Kakarot. Is the and so agent native. What does it mean? It means that we build from scratch. When you want to build without agent, you're like, okay, I'm going to reuse libraries or so on and so forth because you want to save on time. But the agent, they write code faster. So you don't want to bother using library. You can tell the agent, take inspiration from this library, but generate new code. I mean, if at some point, then you get much more flexibility on how you want to handle all the complexities of mixing different parts of logic. They have the knowledge. The agent knows. So you really spend 99% of the time in plan mode, reviewing the plan, what do agents want to do. And the very killer thing, I may stop here because then it's example, it's really macro-intensive code base. So instead of writing a lot of code, we ask the agent to write the macro, so that we can focus as human on defining very high-level things in terms of what we want to prove. And so this might be the last slide then because 2 minutes is very short. Like for the AR, for the table, for example, we wanted to be able to express almost in Markdown the tables and the constraint. So we have asked the agent to write a macro so that we can define all the tables of all the prover with this single macro. And then we generated, for example, a RISC-V interpreter and directly in the RISC-V at compile time, we trace the operation and we generate the witness based on the table that we had in the macro before. And thanks to macro, at compile time, we have a lot more guarantees that you are not mixing up values in different places, in different tables, and so on and so forth. So that's why also we've been able to be quite fast. But 2 minutes was fast as well, anyway.
Okay, thank you. We have a question. Do you also review and understand all the code the agent has written?
Yes. So the code base is 100. I mean, it's very readable. Everyone can go and look at the Stark 5 code base. I have reviewed all the code myself. I don't merge blindly. This is not a front-end side project. This is a real project. But still, it means that it's not the same reading and writing. And the agent has writing capabilities that you don't. And that's so you can focus on the writing on macro. I think the macro is really a big unlocker. Focus on asking macro to the agent.
Cool. And did you find many bugs when you reviewed the AI code?
Not so much. I mean, the AI is not inventing code because if you really spend time in plan mode, you know what the AI is about to do. You don't discover things. But I mean, the design, the function, the input, the output, then you decide, and then they just write it on their own, and then it's fine like that because with Rust, very good compiler, you have a lots of back pressure to the agent. So at the very end, it's kind of easy. I mean, kind of easy.
Okay, wow. Brave new world. Thank you so much, Clément. Next up, we have Fara and Will, who will share Ethproofs updates.
Yep, let me share my screen. Okay, yeah, we pushed a major update to Ethproofs that implemented much of what we proposed in the last call. So prover personas are now live. So basically these 4 prover types. So a team can have one of each of the 4 prover types for a cluster. GPU price index is now live and running weekly. So all prices will be tied to that weekly average. And all historical proofs have been migrated to a quarterly average price. We have new onboarding flows for signing up new teams and signing in as an old team. And that comes with a new team dashboard in the UI where you can both create and edit your clusters. And then also we've added a new external API so you can edit your clusters through that. As Justin mentioned, we have launched a new page tracking guest program diversity, so go check that out. We relocated and revised the pizzas based on feedback from EF teams and others. So proof sizes were changed to match the real-time proving requirements now. Protocol soundness was removed just because it was difficult to audit and kind of verify right now. Security target was changed to soundness, and it will be provided by SoundCalc moving forward. And then we pitched new designs for the security sprint leading up to the next Ethproofs call in ECC. So this is kind of the next chunk of work that we'll be working on. So kind of look for this to start to become live towards the next call. I'll present that.
Okay, fantastic. Yeah, thank
And
you
then
for. Go ahead.
just to follow on, my short update with that is we have a new Ethproofs builders channel. So if you're submitting proofs, you've got a guest program or a zkVM on Ethproofs, or you're getting very close, DM me and we can add you to that. So that's where we've been sort of coaching people on the new onboarding, and we're going to be sharing Figma comps. So a lot of the teams that really like quote unquote have skin in the game, we want to make sure that we're getting their feedback and integrating that feedback into what metrics we're going to be highlighting. And then lastly, in the chat, one more shill for our Ethproofs, ETHCC in Cannes side event that's coming up on March 28th. So make sure you sign up. There's only a handful of seats remaining.
Amazing. Yeah, I feel like the pace of change, I mean, in general, is increasing, but for Ethproofs specifically, we're going to have lots of new widgets, lots of new pages coming very, very soon, which is super exciting. Cool. Any questions? Nope, just a link to the Beast Mode event. Perfect. Thank you, Fara and Will. Next up, we have Kev, who will talk about the zkVM Discord, interop, and all sorts of other things.
Yeah, thanks, Justin. 1 second. I don't have any slides, so I'll just say what I'll give an overview first. I plan to talk about the planning, interop, Discord, and then the guest program. Just one important note as we go into the sort of the guest program talks. So on the planning, as many of you are aware, we published a document breaking down the zkVM project into several sub-projects, gathered feedback, and we've now kicked off most of the protocol-related work with a strong focus on speccing out the requirements and end-to-end integration. Currently, things are progressing well, and later this year, we're planning to have a zkEVM interop event. This could potentially be a side event in Mumbai, just because a lot of people will be there already. It depends on the attendance overlap, and we'll be reaching out sort of in the coming weeks to sort of gauge interest. But either way, we're targeting something close to Q4. On the Discord, to stay up to date on sort of the project, and if you want to ask questions about protocol integration, definitely recommend joining the ETH R&D Discord. There are currently 2 channels, L1 zkVM. This is for like general zkVM things, unrelated to CL and EL integration. Then there's L1 zkVM protocol, which is where you'll see like the EL, CL specking and the integration work. So this is related to the presentation by Jun. In the future, maybe these two will be merged. It just depends on how integrated the zkVM teams become in the future. And the last note on the guest program, as many of you are aware, if you're actually building a guest program, what you're proving is the core STF logic. But last year, we sort of realized that actually you need to prove a bit more. If you're a core dev, it basically means you need to prove the engine API new payload. And if you join Discord, we can sort of talk about it and you can see what the specs will look like. It's a bit of a change, but not too much, but it's something to keep in mind.
Okay, thank you, Kev. Does it have a performance impact, or is it just a minor change?
Currently, it doesn't have a performance impact, but once we go to block-in blobs, it will. Just because you now need to prove that the payload is being chunked into blobs, and this involves potentially doing KZG commitments, which might be expensive for a lot of the zkVMs.
Okay, interesting. And yeah, in the chat, we have a link to the roadmap. Thank you so much for sharing, Ladislaus. Any questions for Kev? Seems like, yeah, you're going to be very active in 2026 at the social layer with all of the various calls and events that you're organizing, which is fantastic. Divya.
Oh yeah, just one question. I think I saw on the Discord something about there being issues with the upstream Rust compiler with regards to some issues. Do you have some idea when it will be sort of mitigated or how it will be?
Could you maybe be a bit specific? I didn't.
I think it was regarding the memory allocation. I'm forgetting the exact term.
I can't
But
remember.
I'll
Might be the
yeah, I'll
unlined
talk in the
access.
Discord. Yeah, the unaligned. Yeah, exactly.
Yeah, I think this is sort of a general. Just to give more context, we was planning to standardize what happens if the guest program was to do like an unaligned load and an unaligned store. I think we've just merged in and said that compilers may have bugs, like the Rust compiler may do an unaligned load, and this is a bug, but it's not a correctness bug, it's sort of a performance bug. I don't know if the issue linked in the chat has been solved, but what we've said is that zkVMs just will need to handle it. So if your Rust compiler is spitting out unaligned accesses, then it won't break the zkVM, it will just make it super slow.
Okay. Thank you, Kev. Next up, we have Dmitry. That's the final quick update.
Hello. Thank you, Justin. So I would like to introduce a new thing that we decided to be necessary inside the EF cryptography team. And the story is that zkVM is a very sophisticated design in general, and having talked with all the teams how exactly they structure the proof, we see that it contains a lot of non-trivial things like how the program traces split into segment, how internally operations are rearranged into dedicated chips, and after that, after you proof this segment as a separate circuit, how exactly you aggregate them using recursive snarks. Well, this is kind of a general paradigm that is satisfied by almost every zkVM, but the details really matter. So how you organize your memory, which precompilers to separate, how you organize these consistency checks. And it appears that the details about this, like dirty details, are necessary for us to reason about the security of zkVM designs. And for this, we decided to ask for like a more formal and more detailed exposition, how exactly the things are done, how the segmentation is done, how consistency is proven, and how the consistency is guaranteed among chips and segments with some specific arguments like permutation argument, lookup argument, and other things. And we believe it should be a document that covers all these things and the details about the recursion, about the details about the statements that are proven at every step of the recursion, and how exactly they combine into the final statement about the correctness of the original program. So we think that such a document should be written. It's not definitely a spec. It contains much more math and more English, and it should be prepared in phases. And on the right, you see an approximate timeline we have in mind. So we have just communicated the preliminary requirements to the teams, and we will publish them very soon. We ask to integrate their circuits and lookups into SoundCalc by the end of February. And basically, we expect the first deliverable, the first kind of superficial thing in 1st of May, which is called milestone W1. And then we soon publish the new requirements based on the feedback from the teams. And the final document ideally should be produced in the beginning of December, collocated with this requirement, the milestone of achieving 128-bit security. Yeah, that's it.
Okay. Lots of due diligence from the cryptography team. This is great to see. Any questions for Dmitry? We do have one question in the chat for E. How did you measure the 3.8 gigahertz, and are you taking into account precompile instructions?
Yeah, this is on the CoreMark benchmark. So we ran Cormark with 10,000 iterations and used a setting that only includes RISC-V, so no precompiles on this one.
No precompiles. Okay, perfect. Yeah, very impressive numbers. Cool. We're going to be starting the 5-minute presentation. So first, we're going to have 6 presentations from 6 different EL client teams, starting with Geth. So Guillaume, the floor is yours to talk about Keeper.
Hey, let me share my screen. And while I do this, thank you very much for letting me go first. I'm sorry to front run everybody, but I've got a babysitting issue. Okay, is that it? Yes. Okay. All right. Can you guys see my my presentation? Okay, perfect. So yeah, I would like to talk about Keeper, which is the guest program from the guest team. The design philosophy is going to be fairly different from the ones you're going to see after in the next presentations. There was a conversation in Berlin back last year, last June, and we agreed with the zkBesu teams that we should implement the Linux interface or at least WASM compatibility. This is not the road taken by other people, but other guest programs. But we think it needs to be zkVMs need to be a general computing platform. So in this respect, the zkVM teams we talked to agree. So we decided to explore this approach for the time being. So yeah, we're not sweating that much, Justin. And where does the name Keeper comes from? It's like a lot of guess projects. It's based on the Mass Effect universe. None of us have played it, but apparently there's those those entities that are quite secretive. So we thought it would be the perfect name for Keeper for the guest program going into zkVMs. Supported targets, because of our choice, our design choice is going to be limited. So far we only support Xyren. We had some successful tests with OpenVM and Powder, but Powder decided to rewrite everything. So we're waiting for the update to see how good the performance is going to be, and we're going to go through the WASM pipeline. We also had a very good conversation with Succinct in Buenos Aires. So we're also going to explore WASM on this side. Apparently, looking for the name. Arbitrum is also interested in using WASM, so that there's a good synergy for us here. The last zkVM we're going to target for the time being is Zisk. We would take the route of compiling for RISC-V64GC, which, as you know, is not compatible with the target. But we're going to make some tweaks and see how far we can go with this. We're only considering 2 tool chains. I assume Nethermind will have a lot to say about this, but for our guest program, where we want to stick to the stock Golang because we know it. The problem is it either requires an OS support or dirty hacks. There's also Tamago, which doesn't really target the platform that is targeted by the other zkVMs. But since apparently it's going to be merged, some of it is going to be merged into mainline. We are also experimenting with it. So what did we do so far? We tested a few hundred blocks, no issue reported. So at least our model is sound enough to continue. And yeah, every time we commit to master, we build a release of Keeper. We don't actually publish releases on our page yet, but yeah, we're working on it. What we're gonna do, therefore, in the future is to try to chase some performance. So add more precompiles, try an alternative interpreter, maybe a Zig one, maybe a EVM one. We'll see. We're gonna try to remove the allocator because the garbage collector is the big the big issue really. And what we would target first is things that could apply to mainline Geth, so outside of the zkVM, so that everything that gets developed is not wasted. And another goal we have is to push, start publishing our proofs on Ethproof with Zyren. So I'm hoping we can do that in the next few months. Yeah, I'm out of time, but that's also most of what I wanted to say. So yeah, thank you.
Okay, fantastic update. And I didn't know about the potential integration there. I realize that these are like probably very preliminary numbers in terms of performance because you don't have the optimizations with the garbage collector and the precompiles. But like, can you share like what is the starting point right now?
Yeah, so the starting point, I mean, it's slow, it's ugly. We're not ashamed to say that our goal is to be correct. So I think what Zyren did, but we don't have the precompiles, like we don't have a lot of precompiles. Zyren made measurements and we're like 20x slower than revm. But like I said, it's only a starting point, and our goal, I mean, we need to be functional, of course, but we want to focus on the correctness more than the performance.
Got it. Thank you, Guillaume. And congratulations. Next up, we have Dragan, who will talk about revm.
Hello, everyone. To be honest, when just asked me to present revm, I was not sure what to do because I think this group is very familiar with it. So in general, I would like to share screen. Just a second. Yeah. Basically, revm started as the hobby project 4 or 5 years ago, and at the beginning, I have like few guiding principles that I want to make to allow me to like guide myself on decisions when I create or modify revm. And I think they're very like even now very important. First one was is of course EVM compatibility. Any consensus bug needs to be squashed. Everything needs to be corrected. Every test needs to be passed. It needs to pass. Second one was speed. I wanted to build very fast EVM that everybody can use. Third one was simplicity. So it's easily used. So anybody that need like EVM execution can just plug it in, plug the database. At that point of time, just send one transaction, and that should be it. And the last one is let's do it no STD. At the beginning, idea was to support JavaScript or CPP binding or anything like that. But in the end, it was very fruitful for zkVMs for no STD support. Yeah, old basically. And basically, it was hobby project at that point of time, this like logo that I created at that point of time. Presently, I think everybody uses revm and zkVMs for a reason. Revm is very like used by all the builders, all zkVMs. It's integrated in Reth. I think additional one topic that I could add in this principle is basically extensibility. It allows something like OP Reth, OP revm to be created and just extend the use revm as the library. This became like very good guiding principle for the future because everything that's made, changed, or found can be like focused in one code base. There was a lot of PRs related to both the improvements to the code base. I think Kev did a lot of those about allowing precompiles to be plugged in with zkVM versions. So yeah, my DMs on that side are always open. If you have something, even if you don't have time to implement it, just saying, hey, this could be good is always helpful. I think that's it for me.
Okay, we have a couple minutes for questions. One question from me is, my understanding is that you're now part of the Tempo project. Does Tempo have any plans for doing zkVM stuff?
Not on me to say anything. So in general, I basically employed by Tempo. Fortunately, I can still work on revm, improve it, basically make it better, make it faster, make it more usable. So I'm very glad that I'm there. Yeah.
Perfect. All of the improvements to revm specific to zkVMs, have they all been upstreamed to revm? And do you feel like there's more zkEVM specific work to be done?
Everything that I know are upstreamed, but there is some things that I don't know. And what would make revm faster in zkVM? For example, allocation is very slow. That basically is feedback that I got multiple times. So using something like bytes or statically allocating before execution helps. But in general, having something like some benchmark or having some flame graph that could be done from zkVM side to show me, hey, this part of the code is not great for zkVMs would be very, very helpful. Maybe that's like big ask, but yeah.
It's great to hear that you're so open to improvements for the zkVMs. And yeah, if anyone wants to improve the memory allocation, that might be a low-hanging fruit for you to work on. And Kev says the main UX benefit that we merged a while back was the trait interface that replaces precompile patching.
Yeah, kudos to Kev.
Cool. Yeah, congrats, Kev. Thanks, Dragan. Next up, we have Iván, who will talk about levm in the context of Ethrex.
Hello, everyone. Thank you for the invitation and the opportunity. I'll be sharing my screen right now. Okay, can you see it?
Yep.
Perfect. Well, I'm going to talk about Ethrex levm and guest program diversity. Let me here. Here's a quick overview of what I'm going to talk. I'm going to talk a little bit about shortly our Ethrex, the current status of our guest program, why does diversity matters, how zkVM teams can integrate with Ethrex, and how they can get involved on that. So Ethrex, it's started as another execution client in Rust, and then we are now transitioning to a zkEVM guest program, which uses levm underneath, which is our implementation of the EVM protocol. It was designed from scratch to be zk friendly. Yes, and it was built for proving. Right now, Ethrex is in production as an execution client and also as a guest program. We are running on-prem ZK prover on Ethproofs, which was this week offline because we were doing some modifications to it, but it is up again. And right now, the guest program has integrations with ZK, SP1, and RIG0. We are finishing the integrations with OpenVM and Pico, and we are planning on integrating a vendor in the near future. And why we stepped in? Diversity matters. The foundation of Ethereum is diversity. We need to do the same for guest programs. Right now, almost every prover is using revm or Reth. There are new guests on here to use, and it will be fine for all zkVM teams that try Ethrex, integrate their zkVMs, and also host a prover. In our repo, we have a great guest program. It was a recent refactor that makes everything easier to understand and to read and to integrate. We have instructions on how to build the elves and also how to integrate your zkVM there. This is more of a call to the zkVM teams to use Ethrex and to collaborate with us. We are very open. At the end of the presentation, I'll share some links to the Telegram where you can find us. We already are working closely with some zkVM teams. but we are open to the ones that we are not currently doing. So the message is, Ethrex is ready. Let's build together a future with a big diversity of guest programs. So these are some of the links. The Telegram, the Twitter. We'll be having a Discord soon for community also. That's it on my side. I don't know if there are any questions.
So you mentioned writing levm from day one, targeting zkVMs. Can you talk about what specific optimizations you've made that are targeted specifically for zkVMs and how that might differ from revm?
Well, there are things that, for example, we are avoiding a lot of the clonings, and our try implementation right now is being optimized to be more zk. The only part that is not that zkVM friendly is our try, but the rest of the code goes really well. We also planned all the modules for the precompiles. It's very easy to implement. It's not like the interface that Geth mentioned earlier. It's a little bit different, but we'll be adopting that in the near future. But yes, the main thing was every zkVM has different precompiles, and it was a little bit messier. We have modules that are separated, and you can switch which backend to use with feature flags, for example, from different zkVMs.
And for the memory allocation, do you have a custom solution there?
Not right now, but we are working on improving it even better.
Okay, got it. Yeah, if anyone has questions, just feel free to raise your hand, ask in the chat, or just on mute. If not, thank you, Iván, and we'll move to Somnath from Erigon, who will talk about Zilkworm.
Hey, thanks for having me. Let me try to share my screen. Okay, so Zilkworm is an efficient, fast, stable zkVM core written in C++. The objectives keep changing, but here's some of the bits that you should know about me. That I've been a core developer for Erigon and quite bullish on zk, and this presentation is on a Ubuntu laptop that goes on to show how much you can do with open source today and not cave into the big tech. But let's just go over what we did for Zilkworm so far. So we're already live on Ethproofs since September 2025. We also deployed the Turbo version, that is SP1 16th prover, which was almost as efficient as the RSP version running Hypercube. We went on to then optimize further to make the Zilkworm Hypercube, and it performed around 2.5 times faster. Eventually, we delivered the smoothest Osaka upgrade. So we were monitoring how the upgrade would work out at the fork boundary. That went well, and now we have 100% passing east. Again, correctness. A little bit about the legacy of this project. Erigon had a project called Zilkworm, which was a full client implementation in C++. Also used EVM1 in its core as the EVM, and it used a state sync model and so on. But the takeaway from that was it was already 30% faster in execution and around 4 times faster in RPC. That goes on to show that that's a very good candidate for the resource-constrained zkVM. Of course, we have big thanks to give to the amazing EVM1 and all the contributors, including Pavel, who's also working on this project. we decided to take advantage of the baseline at least 30 to 200% faster revm on certain lines of execution. There is also the advantage of low memory footprint and the work that goes on the side, like the in-text library for big numbers and so many work things on precompiles. We basically forked it right now in a repository called CPM1, and we'll continue to push changes to that. But how it all came together is this 10 lines of Rust code and an overall CPP project in which we can directly use the CX6 bridge. So Rust basically interfaces quite well with CPP, and you can sort of just plug in the whole Zilkworm in any of your prover system. Of course, we started with SP1. So this is sort of how we just call the state transition function implemented in CPP and just invoke an external symbol on it. Some unseen moments. So these incremental upgrades happened with lots of graph, and we just made sure that on every iteration we have like about 50 to 100% catching up, and then eventually we crossed the speed of revm. And then I think last week we focused more on correctness, so we enabled EESTs both natively and on RV32IM with Kemu to pass the equivalence test that we had in our minds. And further this year, we're going to focus on improvements for performance. Our eventual target is 1 gigagas, have some simplified tool chains, RISC-V, of course, and of course, some performance tweaks and unification on the syscall IO with different provers. So we invite you to visit the documentation page and the project page on GitHub, and I'm happy to take any questions.
Thank you, Somnath. You mentioned the performance improvement relative to revm 2.5 times faster, even using turbo relative to Hypercube. I guess one comment. Sorry, go ahead. What?
Hypercube is faster compared to Hypercube. Turbo is almost the same because turbo is inherently slower.
Right. So you were 2 times faster despite running on turbo. So yeah, one comment here is that innovation at the Geth layer is not just about diversity; it's also about performance. And I guess my question to you is: have you tried doing an apples-to-apples comparison, revm and Zilkworm using the exact same zkVM?
So far we've been able to only integrate the Hypercube and Turbo from SP1. I suppose their Geth program is a derivative of revm. So these are indicative numbers. The exact revm deployment, I'm not sure if I can do that. Maybe with Zisk or something which is already out there. But the indication is that RSP is a fork of revm. I'm not sure how much they carry in the lineage.
Yeah, I was kind of using RSP and revm interchangeably.
Right. Yeah. So this is an app. Yeah.
Sorry, I interrupted you. Go ahead.
It is the same zkVM. Zilkworm Hypercube is the direct comparison to RSP Hypercube. I think that's what they use. If I'm not wrong, Tamir on call and might correct me, but yeah.
So Kev is asking, what is the reason for the 2.5x speed up?
I think hard work trying to profile and low memory footprint. Memory is a premium, actually. I have been told for the prover.
Okay, got it. So I guess if we have these like custom memory handlers, we might partially close the gap with Zilkworm. Congratulations, Somnath, on these great numbers. Next up, we have Gary from Besu, who will talk about zkBesu as a placeholder name.
Yeah, thanks, Justin. Good morning from the US Pacific. I've had enough coffee. I think I'm awake enough. Share my screen. Yeah, so Gary from the Besu team. I've been leading our efforts at building a guest program on the Besu team. I kind of want to give you just a heads up of where we've been and where we're going. Like initially, our goals were to leverage Besu, the code base, and the team, and the Lindy that we have there in a guest program. So our initial efforts were to build a state transition function guest program in Java using Besu components. And we got fairly far with that, and we're building for RISC-V, targeting RISC-V with a GraalVM levm feature. Unfortunately, it's it's OS dependent and linking to a static JDK. We ended up with just massive binaries. We were contemplating, targeting Musel and using static, using shims to get to bare metal. But we decided that that's going to be brittle, and the tool chain would be very brittle. The resulting binary would be large, probably not all that performant, and it would basically destroy any Lindy that we think we have with using Besu as a core library for a state transition function. So we pivoted probably late Q3, early Q4, looking into a native EVM that we could drop into Besu. Our goal in that case would be we would only, as a team, be maintaining a single EVM rather than having a Java VM and a native VM that we would have to maintain. The goal in that case was to kind of limit that so we don't have multiple, duplicate work across multiple EVMs. We got far enough along with that we were doing performance benchmarking, and we found that even with like Java 25 FFM improvements, crossing that Java native boundary, going back and forth between a native EVM and Java for doing callbacks for tracing and things like that, just that native boundary cost just dominated execution hugely. So we decided that really wasn't a viable path either. So late Q4, basically, we decided that we need to go ahead and pivot to another language and another tool chain that's specific to that's going to be able to target bare metal RISC-V better. So we're kind of in the early stages right now. We have recently chosen on the Besu team to use Zig. And specifically, we're bootstrapping with a project called zevm that is a revm-derived port of revm to Zig. And we're making good strides towards that. We have a working EVM implementation already, and the guest program is reading and writing, inputs, state witnesses, and so forth. And we're kind of moving towards. We've got partial precompile implementations, and our goal is to have Fusaka support, like kind of alpha quality Fusaka support ahead of, ahead of Glamsterdam. That might be a bit of a stretch goal considering where we are right now, but that's currently what we're targeting. And then after that target, we're going to be targeting just general, protocol schedule, forward-looking compatibility post Glamsterdam. Also, we are currently building with Zisk. So we're not tightly coupled to Zisk, but we're really only focusing on Zisk, especially for like the CSR precompiles and so forth. And in our kind of final spike, we're looking to do multi zkVM support, standards compliance, and an extra stretch goal would be to have an abstracted EVM interface so that we could potentially plug in an additional EVM. But I mean, at the moment, we are working with Zig, zevm, and Zisk. And a little bit about where we are right now. Like I said, we have some of the cryptographic accelerators implemented for Zisk. We still have some outstanding work to do on some of those precompiles. We're integrating at least the reference state tests currently. We have work to do on getting KCG commitments, verifications implemented, system contract executions, withdrawals, all of the Fusaka specific protocol schedule stuff. But that's, we're making good strides. And we recently started having talks with the Zeem team to potentially collaborate on a state transition function so that we could have, a Zig specific stack from bottom to top in the future. And then also we're collaborating with Linea on block proving. And that's pretty much where we're at the moment. We're going to be MIT licensed, and we'll have a public repo to share soon. Stay tuned.
Okay, amazing. Kev is asking, what have you found hard so far about re-implementing the STF for zkVMs?
I think the most challenging aspect we've come across so far is the memory alignment issues when we try to implement precompiles and cryptographic functions that don't have accelerators built in, trying to bring in third-party libraries, Rust or C++ libraries, static blocks and things tend to kind of mess with the memory alignment. That's really kind of been one of our current stumbling blocks, but I'm sure there'll be more to come. But that's at our current state of development, that's what we found the most challenging.
Okay, perfect. And when you mentioned zevm, I just wanted to clarify, there's like 2 Zig implementations that I found, one from Jordan Coppard.
Right.
Is that the one?
It's not that one actually. It is an independent contributor who's, I think.
Is it Raúl Jordan?
No, it's Lodge is his GitHub handle, and zevm is like it's fairly early but fairly complete. I could provide a link in
that'll be helpful.
on the chat here.
Thank you. Okay, great. As a side note, the implementation from Jordan Coppard is also being worked on by Guillaume on the Geth team, and there were like very, very early discussions of potentially having that be integrated with Geth. I don't know if Guillaume is Guillaume on the call? He may have had to leave.
I'm gonna have to leave in just a sec, but yeah, it's still an option. But so far we're going to try to make Geth faster while zevm, matures.
Okay, got it.
Yeah, we've considered, one of our stretch goals, as I mentioned, is to have a more abstract interface around our EVM implementation. So we could potentially change that, be it something derived from zkSM from Linea or zevm or one of these other projects. But that is a bit of a stretch goal at the moment.
Okay, very interesting. Thank you so much, Gary. Next up, we have Maxim from Nethermind, who will talk about NethEVM, the implementation of the EVM in Nethermind.
Hi, do you see me? Do you hear me?
We can see your video.
Okay, one moment. I will share the screen.
Yep.
Do you see my screen?
Yes.
Yeah, perfect. Okay, so I'm going to talk about Nethermind implementation. So what we have achieved so far, we have made execution witness, we have developed a stateless executor, we've made a minimal EVM binary, and probably the biggest chunk of work in terms of iteration was RISC-V 64-bit compilation and just a little bit smaller ZISC integration. I will talk about some specific points of this work. So as for stateless executor, it's still implemented fully in C#. It's based entirely on Nethermind client code base. It uses, of course, some conditional compilation to trim unnecessary and incompatible code, but overall it's still the same. It's fully native and it contains no dependencies. After we built our binary, it's a binary which we can run still on Linux in some ways, if we have just a bit different linker script. But It contains no single system call, and it can run on ZISC and other zkVMs when we implement them. Then such stateless executor can call to zkVM IO, whatever zkVM we use, and it can call to zkVM precompiles. That's what is implemented, and it works for us. As for toolchain itself, I will tell again that we have adopted Alpine Linux. We needed it just to build net runtime because, well, it naturally needs a lot of Linux packages, even if they are not really needed. It's a bit hard to trim all dependencies at this stage, so that's why we did it. But we changed compiler mode to RISC-V64 IMA. We disabled assembly usage, truncated floating point usage, and fixed lib and wind frames, and did many small other fixes. As for native layout, and native layout is a ahead of time compilation, actually. So to compile C# to native RISC-V64 bit binaries, we employ RISC-V64 code generator, which is already implemented within .NET. First, it wasn't ready, but now it's even released, so it can be used in .NET 10. We add many patches. First, we remove eventing and all other redundant parts. There are a lot of different models that are not really needed for us. We add zero library, that's some simpler versions of some functions. And we also unfloat just-in-time code generation, lib and wind, stack saver, and other parts which depend on floating points. Of course, we can't use floating points and we don't really need them, so we trim them. Also, we clean up big integer calculations because they still rely on floating points, but we of course needed some precision at this time. We have developed our fork of bflat. In this fork, we still build IL code as usual, no changes really. We add some precompiler definitions and other stuff, but in general, it still follows IL compiler flow. We add extra net libraries. For example, target zkVM libraries for input-output, precompilers, and whatever. The biggest part is extra native libraries. We add a new PAL, a new RHP, it's it's .NET models. We add random number generators, UTLS implementations, C++ shims, updated Bootstrap, and which is also important, a garbage collector, a new memory allocator implementation as well. And then we relink it properly. So we just use wrap linker option, and by that we can integrate whatever we want quite easily, and it works, in fact. We start with native start entry point, then we run Bootstrap, then we run libc, then Bootstrap, and where we initialize everything. And then we run just a C# main, which actually does a lot of calls into our modules implemented on top of bflat fork, doing custom applications and whatever else. So, and also in order to make it work, for example, in ZISC, we had to do some extra work. For example, it doesn't tolerate data inside code sections. I know there was some work done, but still we had to implement wiping data from code section. It worked. So yeah, that's it. Any questions?
Okay, thank you. Kev, thank you for your questions, Kev. Kev asks, how many cycles does runtime initialization take?
Oh, it's very good questions. I know the counter goes over millions, but I can't tell precisely because it depends on the code size, of course. Runtime initialization itself is quite small. But every additional module adds static constructors and whatever else, so it depends. It's still changing every time we edit stateless executor.
Is it fair to say that you could just run the initialization once and then take a snapshot and then load that checkpoint?
I'm not very good at stateless executor implementation itself. I'm more about C# compilation. So, but as far as I remember, right, it's what was implemented by our team.
Okay, and Kev also asks, is the garbage collector now just a bump allocator, or are you still freeing objects?
We're not freeing objects right now. We don't care about it. We allocate objects just like from the top to the bottom right now. Later, if we need it, we will implement freeing, but it's not needed right now.
Okay, and do you have a max amount of memory that you can consume?
We have some preset available. I think it was 100 megabytes for now, maybe even more, but we can change it every time we want. It depends on the virtual memory size that is available. So we are not quite limited on that.
Okay, and Kev also asked, why did you also have random number generator as an extra lib?
Oh, it's a good question. Previously, it was using OpenSSL, and of course, we can't use it this way. But eventually, if random number generator is available as precompiles in specific zkVM, we will use it. So no problem.
And I guess a question for me, can you try and quantify the invasiveness of all of the changes that you've done to the tooling and maybe the probability of a critical bug being introduced by modifying the tooling?
Well, we don't modify tooling itself for sharp compilation. We change some functions. We do quite safe changes in most cases. There are not very safe, in my opinion, changes regarding object layout inside the garbage collector, but it's all testable. We can just perform many tests, see how it works, and perform some validation through other ways. So it should not be a big deal.
Perfect. And do you intend to integrate with Ethproofs soon?
Yes, as far as I remember, we have just another team member who is working on it. So.
Okay, perfect. Thank you so much, Maxim. So this concludes the presentations from the existing consensus layer teams. Now we have alternative EVM implementations, and we'll start with Bruce from Monad, who will talk about their EVM.
Hi, thank you for the invitation, Justin. Just looking at my screen here. Cool, fantastic. Yeah, it's a pleasure to be here. I'm here from Category Labs. We are the sort of primary maintainers of the monad execution.
I'm following some master thesis. Okay, so
sorry about that. We just muted someone.
Thank you. Yeah, we are the sort of the primary maintainers of the monad execution and consensus clients. The monad EVM is a GPL3 C++ implementation of the EVM. We support everything up to Osaka. We tested against replaying the whole of Ethereum history up to, I think, a block in the range of 23, 24 million. I don't know where our sort of downloads are at the moment, but it's in the sort of low 20s, our replay compatibility. The VM is live on the Monad mainnet. We're running at a sort of notional supply size capacity of 500 million gas per second throughput. The execution client is written in C++ and is optimized pretty heavily for the specific Monad validator specification. And so we have things like a custom state database for accessing raw NVMe block devices. There's a custom encoding of the database there. We've got a really fast bytecode interpreter for the EVM based on guaranteed tail call optimization. Transactions are executed optimistically in parallel, detecting conflicts and retrying. The database is written such that retries of conflicting transactions are really cheap because you've already warmed the database and the stuff is cached in the drive and in memory. And we've got what we sort of believe is one of the best specialized x86 256-bit integer implementations as part of the execution client. We're pretty early on in our progress towards becoming a zk guest. We have our interpreter compiling to a RISC-V ZISC host already. So we've got somebody working on that, and we're sort of at the level of making proofs over single opcodes at a time and figuring out the toolchain support, because while we're written in C++, we're kind of at the bleeding edge of toolchain support, even for x86 code gen. And so we're testing the boundaries of what you can do with available RISC-V toolchains. And at the same time, we're beginning to figure out the practical steps that we need to turn our database and sort of in-memory state representations into something that we can use for witness-based stateless execution in the client. Everything is open source. Like I said, it's a category labs/monad. We're pretty early on in the zk journey. We're hoping to move pretty quickly and get towards a working guest program Q1, Q2, and we're hoping to, at that point, get integrated into Ethproofs and have something that's runnable and hopefully pretty fast. Cool. Happy to take any questions.
Perfect. Thank you, Bruce. I guess we were talking about how Zilkworm is maybe 2.5 times faster than revm. Zilkworm is in C++, at least EVM1. How do you know how your implementation compares to EVM1?
It's been a little while since I ran the benchmarks. When we wrote the interpreter, it is on sort of pure compute benchmarks, comparable or faster to EVM1 on basically everything that we ran it on. Obviously, as you do larger programs in the EVM, like host and state start to dominate your execution time, but for raw execution, we think it's as fast or faster than EVM1.
Okay, got it. I guess all of the optimistic execution, that's not relevant, right, for zk EVMs?
Yeah, so this is we have a lot of like systems code in the client that we're going to have to figure out abstractions for and rip out. But this wasn't necessarily written in a zk friendly way, and so we're going to have to sort of do a lot of practical work to, I guess, have both coexisting in the same code base to find the right engineering abstractions to let that happen.
Right. Kev is asking, what is the main motivation for Monad's investigation into guest programs?
It wasn't something that was sort of hugely on our radar until I guess you got in contact with us and said this is something that's interesting. I think we're basically interested in maintaining Ethereum compatibility to some extent. We have all the spec tests, all of the replay passing, and I think a general sort of alignment with the Ethereum ecosystem and roadmap is in both of our interests here.
Very nice. Yeah, and I learned on our call that even though Monad has some differences, it's not strictly EVM equivalent. You maintain a version of your implementation which is strictly equivalent to L1.
We implement all the features that are, so for instance, Monad L1 doesn't have blob transactions, but we have full support in our execution layer for running blob transactions. So we take care to be like EVM compliant even when it's not like directly commercially relevant for the Monad L1.
Thank you so much, Bruce. Next up, we have
Raúl.
Raúl
Thank you for the invite.
from the, well, he'll be talking about the Filecoin EVM, and he used to be involved with Filecoin.
Hey everyone. Yeah, thanks for inviting me to this. These days, I work at the Ethereum Foundation. I lead the peer-to-peer team and some scaling efforts. But so this is going to be about a past life that I had, where I was deeply involved in Filecoin, and specifically the Filecoin virtual machine project, which also shipped a EVM compatible runtime, and that's what we're going to talk about today. So why? So I was chatting with Justin a few weeks ago, and we were talking about guest programs and kind of the difficulty in extracting the pieces that are needed from existing Ethereum clients to actually minimize what needs to run in the zkBesu environment, and kind of like, how tangled things are, just because the EVM runtime specifically were not built to be extracted or to be sandboxed and so on. So things are really tangled. So the challenge generally, as I understand it, is clients are monolithic. They're built for a bunch of things. The EVM runtime is usually coupled with a client, and there's large dependency trees and runtime overhead to prune on that path to making them run within a tighter zkVM environment. So the Filecoin EVM is actually built on the Filecoin VM. So FVM is a WASM-based hypervisor. Originally, we had decided to run multiple runtimes, or to host multiple runtimes, using WASM as kind of like the intermediate instruction set, essentially. And the first runtime that was shipped in 2023 was the EVM runtime. So this is called FEVM. Just to give you kind of like a very quick overview, the Filecoin, the FEM has this notion of actors, and the FEM provides a contract to actors, which revolves around providing syscalls, which are very nicely packaged calls out to the host that perform things like I/O, crypto, randomness, and things like that. The FEM does gas accounting by weaving in basically transpiling WASM bytecode and weaving gas accounting logic and the halt conditions and so on statically. But the state is represented in Filecoin state model, which is based on IPLD, which is also used in IPFS. So this would be one part that would need to be translated. So the EVM runs as an isolated WASM actor with a very clean syscall boundary. So all the side effects and all the calls to the environment and so on are very nicely packaged. And all this runs through trade abstractions. This is a Rust code base entirely written in Rust, so compiles to WASM, of course, and also to RISC-V5. I tried it today. There is no shared state, no global dependencies, and so extraction would be pretty straightforward. Specifically about the EVM runtime, it is a very small program. It is already no STD, and it compiles to RISC-V. As I said, it has all of the externals are very nicely abstracted in traits, and because it runs in a sandbox environment, it has no GC and it has predictable execution. We actually restricted the FEM restricted the WASM instruction set and kind of like the features, the WASM features, to remove things like floats and remove things like threads and so on, and SIMD that would introduce non-determinism. So this like assumes that, and it is LLVM friendly. It's also entirely Ethereum compliant in terms of basically everything, all the way up until, so we started, because this was launched in 2023, we started with Paris, with a Paris fork onward, so it does not have any historical baggage, but it does have the newer features like per0 and transient storage that have been introduced since then. So I do think that it is up to date with the current environment, so that's nice. And it is entirely compliant in terms of gas accounting, halt conditions, and so on. And it does have all the precompiles that Ethereum requires. So this is just some of the key structs that are behind this implementation: system struct, the storage struct. Some of these, these are structs and storage is a trait, and specifically added it here because it's one of the, if somebody wants to use this EVM runtime and build on it, this would be something that we'd need to change. So yeah, so in terms of potential next steps, the idea would be to extract the EVM runtime, remove the Filecoin specifics, which are not that many. I think this could be done very quickly. Compile it to RISC-V and smoke test under a number of variants. And the important bit here is adopting the MPT storage model, because right now the storage is based on IPLD and HAM. So yeah, and then benchmark compare proving costs and so on. So like starting the cycle. If somebody's interested in doing this, very feel free to contact me and we can take it from there. I'm also in my own time doing a little bit of this work, but it is not my primary focus. I can help out any teams that might be interested in taking in experimenting with this.
Okay, thank you, Raúl. I didn't realize there was a different tree. Kev is asking, is it up to date with Osaka?
Yeah, I think yes. I think with the exception that the Filecoin network does not support blobs in the form that they exist in Ethereum. So there might be some differences there in terms of some specific opcodes, but other than that, it should be up to date. And if not, it should be pretty trivial to bring it up to date.
Cool. And who would you say is the main person on the Filecoin side of things working on this?
Yeah, so you can contact me and I can route you to the right person. Just feel free to do that.
Perfect. Cool. I see no more questions. Thank you so much, Raúl. So next up we have Evgeny, who will be talking about two separate EVM implementations that he's been working on. One in the context of NEAR, the Aurora EVM, and a second one called the Swift EVM.
Do you see my screen?
Yes.
So hello, thank you, Justin, for the invitation. So today I am presenting the Aurora EVM in the context of the emerging zkBesu landscape. I will briefly outline the specifics of Aurora EVM and its place as a zkBesu Geth program candidate. So, why is Aurora EVM specifically suited as a Geth program? And what are the key features? First, the stack. Aurora is written in Rust in the context of zkBesu. This ensures the maximum performance and full tolerance, and it is under the MIT license, which opens a broad possibility for community usage. Second, it is maturity. This is not a research prototype. The Aurora EVM has been running in production on the NEAR protocol since 2021. It currently secures $10 million. This means we aren't just proving code, we are proving a code base that has already handled millions of real-world transactions without failure. We are proving battle-tested code for the zk context. Next, let's dive into the performance constraints. Running the EVM inside zkVM is computationally expensive, it is obvious. The proving time correlates directly with number of execution cycles. Here, Aurora has unique architecture advantage. Because we originally built this for the NEAR blockchain, we were forced to optimize strictly for WASM execution limits. We had to optimize the instructions count for every operations to fit into NEAR-GAS model. And I think this pre-existing optimization for WASM maps incredibly well for the circle count constraints of zkVM. We effectively inherit years of low-level optimization in that count. Furthermore, correctness is paramount. We maintain 100% compliance of Ethereum execution spec test. We support all hard forks, including the latest Osaka. This guarantees the proof generated of our Geth program is mathematically equivalent to standard Ethereum state transition. So, what is the current engineering status? We have successfully compiled the full Aurora EVM codebase as a zk Geth binary. We can currently execute multiple transactions with the zkVM and generate proof to prove for our output. The core execution flow is functional. The next phase is scaling this to full block validation. We are engineering the flow to handle the entire block context execution. We have set a conservative timeline to finalize the architecture to Q3 2026. This allows us to address the overhead challenges and optimize the performance. And conclusion. Aurora EVM is in a good state of readiness of the zkEVM gas program. We are leveraging a production-ready, highly optimized Rust implementation as fast track for development, verification, competition. Thank you.
Thank you, Evgeny. It's very interesting to see WASM as a theme for several of these implementations. Any questions from the audience? I guess one is, can you talk more about the motivation for the Near ecosystem to be looking into zkEVMs?
Actually, one of the most interesting motivation, as I said, is because we inherit years of low-level optimizations, and we try to use some different solution for our Aurora engine, and we realized that we are in quite good condition. It means that at the moment we can't use any other solution because we are optimized for cycle soak execution. It means that we can feed for zkEVM excellently. It is my own opinion.
Okay, perfect. So all of the gas golfing that you've done in the context of the Near smart contract applies here again. Makes sense. Cool. Well, I'm not seeing any. Go ahead. Oh, no. I'm not seeing any other questions. So I guess we could move on to the Swift EVM.
Sorry.
No worries.
They should change that.
I guess one side note is that even though the Aurora EVM is securing 10 million now, at its peak it was securing, I believe, billions of dollars, potentially close to $2 billion. So yeah, it's definitely stood the test of time.
Really sorry that is for some reason not show my presentation in my slides. Quite sorry to.
Alexander, do you want to comment about the total value secured in 2022 while we wait?
Yeah, you're absolutely right. The amount was extremely higher in 2022. It was when Aurora just released, and of course, in price for Aurora token was much higher, and amount of value was locked much higher than now. Yeah.
And can you talk about audits that have happened to Aurora EVM?
Yes, we did audit with Audit One company, but at the same time we have a bug bounty on Ethproofs, and we constantly respond to some reports that we receive, and I mean that we constantly under attention of some hackers, and yeah. Unfortunately, the bad thing that a lot of reports are generated now by AI, and it's a bit annoying. But yeah.
Okay, got it. Thank you. Evgeny, we can see your slides. The floor is yours.
Yes, I'm really sorry for pause because it was a second presentation and it was hard to find it. So thank you again, Justin, for the invitation for my second presentation. Today I am presenting Swift EVM in the context of the zkBesu context. This is my personal initiative. Swift is the native language for the entire Apple ecosystem, extending actually also embedded devices. Currently, the blockchain ecosystem in Swift is almost non-existent. You probably know it. Swift EVM aims to be a foundation building block to change that, to unlock that unique niche. Next, the rapid evolution of zkBesu opens new doors for emerging projects. Nevertheless, Swift ecosystem is currently a blank canvas for that regard. Swift EVM can serve as a catalyst for a new whole development community. We are effectively expanding the boundaries of where Ethereum can go, bringing to new platforms and environments. The core feature of for that project, it is fully native Swift implementation. To achieve high performance and good points, we had to build essential low-level libraries that simply don't exist currently in Swift. So also it is in MIT license, opening broad possibilities for community usage. The project is currently in an active development phase, and it is technically in a quite good shape. So Swift EVM has no analogies. It is the first native EVM in Swift language. We pursue uncompromising, aggressive optimization, something rarely seen in typical Swift apps, to ensure maximum performance. It is truly cross-platform, running on Apple devices, Linux, or Android, WebAssembly, and also RISC-V because it is used levm as a backend. Uniquely, we maintain 200% test coverage. And this is an exceptionally difficult standard to achieve, but it allows us to verify every single execution path, guarantees absolute reliability. Regarding the zkBesu gas program, we are currently in research and development stage. The biggest challenge technical challenge in this case, it is a lack of native Swift zkVM runtimes. Our roadmap is optimistic. We are preparing the architecture for zkVM's integration targeting to 2027 for a functional solution. And conclusion, I am inspired by the idea of expanding the EVM horizon. I truly believe Swift EVM will play a vital role in bridging the gap between the Ethereum and Apple ecosystem. Thank you for your attention.
Thank you. Kev is asking, what is the ISA that the Swift implementation targets?
Oh, actually, it is GC for currently I tried for RISC-V 64GC. Also, I want to mention that previously I created formal specification on F# and it is open source in GitHub. So I'm quite convenient with RISC-V and also tried it in an FPGA implementation. And in Swift context, currently I tested compilation only for 64GC, but it is no problem because as you know, as we used levm backend, it is the same backend as Rust, so it is no problem at all.
Got it. So I guess in theory you could compile down to RISC-V, sorry, to WASM if you wanted to as well. Oh, yeah, got it. Also wondering whether Arc is a problem in terms of performance for Swift. Probably Swift will emit more RISC-V instructions than C or Rust.
Not sure.
Got it. And Evgeny, how long have you been working on this passion project of the Swift EVM?
Oh, it is was started in 2024 on September.
Okay, got it.
And why I started this, it is probably quite important because I maintained our EVM, so I have quite good context of EVM and execution layer of Ethereum. So I was quite inspired with that, and I think unique niche for new implementation.
Yeah, and it's amazing to see so many contributors write their own EVM implementations. And today I learned about 2 new ones in Zig, which is fantastic. Thank you so much, Evgeny. Next up, we have Wei Tang, who will talk about the Rust EVM in the context of Polkadot.
Hello. Yeah, so I think I didn't prepare any slides. But for Rust EVM, that's actually a project that existed for a really long time. I think it's probably one of the oldest Rust implementation that is still being maintained. The other one being Party Ethereum, which we now know is unfortunately fully died already. But for Rust EVM, I think I don't have much experience with zkEVM, but I actually want to try to do some integration and see how it works. One thing that I think would be of interest is last summer we did a 1.0 release, and within it we have a new kind of a new generic design. In it we have a new, I think a quite well designed call stack. So the new call stack would allow you to you can allocate the call stack first on stack and then on heap, or you can do that interchangeably. I think some previous team mentioned that they have some problem with memory allocation. I think this could be a point that could be beneficial. So hopefully I will try to tweak some of those parameters and see if it give me some performance improvement. But that's from me.
Thank you, Wei. You mentioned that this implementation is very old. Can you talk about the total value that it's currently securing?
I mean, it's I don't actually have the value. It started as what's called Sputnik VM back for Ethereum Classic. I think in 2017, and then a year later, there was something wrong with the team, and the project became generic, and I rebranded it to just EVM because we have the name. Afterwards, I think there are a few teams that forked the 0.x version to use that in production. I recall there's Etherlink, and also I believe the Aurora EVM is actually a fork of Rust EVM. But of course, they did a lot of new changes afterwards, which become totally independent. And we also use that sort of in Polkadot for there's a few parallel channels, the Moonbeam, and some of them use that, but Polkadot, they have some politics, and they are doing quite big pivot in their direction, so that could change, the situation could change. But the 0.x, they are indeed used by a few production channels. We have the new release 1.0, which is quite new, and I don't think right now any production channel is using that. But hopefully, I will try to improve that and see how it goes.
Got it. And if I understand correctly, you're not directly associated with Polkadot. You may be more of a independent.
I'm no longer associated with Polkadot anymore at this moment.
Okay.
Yeah, but
So
I
guess,
was. So
what is the motivation? Go ahead.
Yeah, I was working with Party for I think 4 or 5 years, and also I'm the maintainer of the Polkadot Frontier project, which is basically the core, the backbone of all the Polkadot EVM stuff 2 years ago at least. So.
Got it. And what is your motivation for keeping to maintain Rust EVM now that you've left the Polkadot team?
The Rust EVM it predates Polkadot. It predates even the time I joined Party. So it's kind of a really long-term hobby project for me. It doesn't directly relate to Polkadot. It's really generic. I also try to keep everything really generic. I think it's the oldest Rust implementation, so I think it's really good to keep it there and well maintained. Yeah.
Got
so
it.
It's just mostly, I think it's mostly a hobby for me.
Understood. Love the enthusiasm and the passion project. Next up, we have Olivier, I believe.
Yes.
Sorry. Okay, go ahead.
Thank you. Hey, everyone. Can you see my screen? It should
Yes.
be a presentation.
Yeah.
All right. Thank you. So yeah, let me talk about Linear's zkVM. So I'll start by just explaining in a nutshell what it is we have. First of all, we're zkEVM, so we provide a direct arithmetization of the EVM instruction set, rather than, let's say, a RISC-V zkVM. We use a lattice-based proving system called Vortex, which runs on the CPU currently, which provides us with 128 bits of security and also handles all of our hashing internally, so SHA-2, SHA-3. For everything else, we use optimized circuits, so GNAC circuits, for all the precompiles and cryptographic operations, such as signature verification, etc. And the whole bundle of that is basically linear zkVM. I'll also just give a very quick timeline. We had our mainnet launch in August of 2023. We became fully proven only in February of 2025, but in the interim, we've on the London hard fork, but in the interim, we've upgraded to Osaka. All right, so let me talk about basically client diversity and the strengths that we see in our approach with respect to that. So the first point I want to bring up is that we don't suffer from this compiler black box issue that is something that's being talked about. We directly prove the execution of EVM bytecode and of the state transition function. Our constraints reflect directly opcode semantics and the architecture of the EVM, from storage to memory layout, etc. This is true also of our traces, which both in structure and in contents directly reflect the execution of the state transition function, which for us is Besu's EVM. And as a consequence, we don't have a notion of system calls or interacting with the Linux ABI at all. We also, by virtue just of the fact that our stacks evolve completely independently of other zkVM stacks, we have no correlation failures to be expected with anyone else. We also directly, by virtue of us directly proving EVM execution, we have substantially smaller traces. Another fact is that, for instance, for catching like certain calls to precompilers, etc., since we have a explicit understanding, basically we know when it happens in terms of our constraints. It's very natural for us to basically redirect data, etc., to specialized circuits. So the integration with these custom circuits is actually quite natural for us. So I also want to highlight, so those are the strengths that I see in terms of our approach with respect to providing diversity, the strongest being potentially this no correlations, no failure correlations. But I also want to highlight some unique complexities that we faced and that we actually overcame to a large extent. Those complexities being the EVM itself, the fact that it's a moving target due to its evolution and hard forks, etc., but also just the history of how the project developed and sort of very eclectic kind of constraints. All of these were sort of salvaged or overcome through design choices by basically compartmentalizing a lot the complexity, but also on a constraints language level. We've made great strides by introducing this constraints DSL, which we call zkAssembly, and which will figure prominently in what comes. All right, so in terms of the EVM and its complexity, a lot of that complexity will be common to basically any zkVM. You have to manage call frames, RAM and ROM, this sort of stuff. As already mentioned, we don't have this notion of interacting with an OS. So that's makes our lives somewhat easier. We also have this idealized model of memory, which is that of the EVM itself, where memory are totally disjoint from one another. There's no notion of reallocating memory or anything. Memory belongs to a frame, isn't shared, and is essentially infinite in some sense. The real complexity or real substantial amount of complexity comes from Ethereum itself, in particular its state, managing the accrued state during the execution, but also the machine state. So everything around gas, warmth, refunds, opcodes themselves, the state, rollbacks. The matter of the fact, though, is that this complexity or this problem is essentially completely solved for about a year, ever since we had our fully proven London release in February last year. And in terms of us shooting at a moving target, so following up, keeping up with our hard forks, etc., that adds for us a development overhead because we have to, hard forks mean changes in EVM instruction set or the semantics of opcodes or new transaction types, etc. We've been able, regardless, to basically catch up over a period of about 9 to 10 months to the latest hard fork, Osaka, and a lot of that velocity actually came from us using or transitioning away from the old way we were writing constraints to the zkAssembly way. And this has basically sped up development and is going to continue as we transition fully towards zkAssembly. And so, this is my last point, this sort of historical development of our project. If you look at our spec, it's very clear that, for instance, we were anchored very strongly in we had very strong assumptions about the underlying base field of our arithmetization, for instance. And this seemed like it was sort of keeping us in a particular arithmetization. But basically, thanks to these progresses we made in our language DSL, etc., we were able to, or we are currently able to, basically reinterpret these existing constraints and move away to Koala Bear, which we will be releasing relatively soon. And another point is that everything that's been written in zkAssembly, and at this point, most of our arithmetization is in this DSL, is by construction actually field agnostic. So it has no notion of an underlying field. All of that happens in a sort of a constraint compilation step that comes afterwards. Yes, so basically the takeaway is that we're fully moving towards the zkAssembly stuff. We want to apply this both to the precompilers that I mentioned earlier, which are currently written in Gnark, but also the hash functions that are managed by the prover. And another reason for us moving in this direction, besides field agnosticity and ease of maintenance and upgradability, is that it has allowed us to integrate with formal verification tools such as Pickers, which previously in our old system was not really possible. And we are baking formal verification methods into the language itself. Yeah, and I just finished with a bit of a roadmap of what's to come. Yes, I guess I'm done.
Great, thank you so much. Great to see Ethproofs integration for Q2. Couple questions from Kev. Curious how you debug logical bugs. For example, if you're implementing an EIP and it's not passing Ethereum tests.
So this is, in some sense, it's relatively straightforward because we have these traces that are a very faithful reflection of what happens inside of the state transition function itself. So we can basically inspect the traces and see what goes wrong. Typically, it's typically when we get to that part of the project debugging, let's say the changes in semantics of mod X for the pricing of this opcode, etc. It's a relatively straightforward, even a little tedious, but it's a very straightforward path where basically by visual inspection we just understand where our tracing goes wrong. It is the in some sense the most fun, but also the least difficult part of implementing, let's say, a new EIP.
Got it. And second question: do you have performance numbers for the STF?
For the STF, so we're using Besu's STF. Do you mean for the prover or for the?
He probably means the prover. That would be my guess. Yeah.
Yes. So our prover is currently running. Our conflations take about 30 minutes to prove. So we're still a ways from real-time proving. Yes, but as I said, we are currently running on CPUs. Our goal is to basically upgrade our constraints to become parallelizable, which is yes, it's part of our steps to the real-time proving roadmap that I mentioned at the end. Yeah, and we also hope to get some significant performance boost from transitioning to a small field koala bear.
Nice. Seems that koala bear is becoming more and more popular. And yeah, Kev is asking, is that with continuations? And Alex replies, with continuations, we can do less. Okay, we're running out of time. We have 2 more presentations. Thank you so much, Olivier. The last one is interesting. It's from Carl. It's a implementation of the EVM in ROC, what used to be called COC, and it's in the context of formal verification. So Carl, the floor is yours.
Okay, so yeah, so hopefully you can see my screen now.
Yes.
Okay, good. Yeah, so I'm Carl. So I'm an academic researcher in Sweden. So this is more work. I call it an EVM specification, but I would say that's kind of synonym in some sense for implementation or definition, right? So just to give you a little bit of background, so the ROC prover is, I would argue, a form of programming environment, but it's a bit different from a lot of other like regular programming languages in that it kind of doesn't compile to anything out of the box. So it gives you a very powerful typing system, but then you sort of get something that is akin to Haskell without the IO monad. And it's very popular, or rather popular, among researchers who do programming languages and reasoning about them. And I guess one of the points here is that it also supports extraction of code, so you can sort of go from a definition in ROC to a C program, and also further to a RISC-V program using a verified compiler like CompSearch. And yeah, it's been around for in some form for 40 years now, around, or a bit more. And usually there are kind of releases every year that accumulate new changes and so on. And inside of ROC, so it has a big ecosystem, and one specific point is the mathematical components library. So this is kind of a replacement for the standard library of ROC, which is, many people would argue, not the most coherent library. So MathComp is much more coherent, and it's very well designed. So it deals with mathematical structures like groups and so on. And there is also a tool for kind of helping you to define your own structures called Hierarchy Builder. And I guess here is where it sort of diverges a bit from the implementations we talked on so far. So this is kind of optimized for proof, so mathematical proofs which are machine checked. And yeah, I mean this library has been used a lot for math and CS. So our goal here in this project was to essentially define a canonical definition in ROC of the EVM to be used, for example, by other researchers, but also for people who are using formal verification and so on. And again, the focus, at least for this definition, is ease of reasoning rather than execution. So I view kind of execution as a separate step where you take these definitions and refine them in a proven way. And then you may get executable codes. You can use verified crypto and so on. And the point, the goal is to maintain this as all of these kind of ROC itself evolves, and also MathComp and the EVM. And yeah, hopefully it can be used by a lot of researchers and so on. And hopefully we can also release versions of this so people can use it as a kind of reference for when they are kind of, for example, verifying smart contract languages and so on. So we will see how that works out. It's more a social matter. So this one of the components of this formal definition is a library for machine words. So this is like a way to reason about machine words in an abstract mathematical way. So I just show you a very small fragment here of a SHA definition. So they are kind of meant for being understood by, I guess, mathematicians and computer scientists, and then they can sort of use them to refine, for example, for performance. And this is licensed under MIT. So our, or at least my work in progress definition of this EVM, that's licensed under Apache 2.0. So you can see the public preview here on GitHub. I'll post a link in the chat. And we're using this old definition in a meta language called EVM by Yuichi, who used to work for Ethereum Foundation. So that's at least my reference point for kind of see if it can be proven to be equivalent. And we also, of course, want to test with the usual tests, but then we need to refine it first. So hopefully, so just very quickly, we will. That's work by my colleagues who have a tool chain basically for going from ROC code to verified efficient code, and also we want to use automated refinement proofs for this. So that's it.
Thank you, Carl. So just to make sure I understand, you have your own formal semantics of the EVM in ROC. You're trying to prove that it's equivalent to Yoichi's lem EVM. And then assuming that these are equivalent, that could potentially act as a good base for the definition of the EVM. And then we have these like certified compilers that could allow us to extract C programs that we can run efficiently on.
Right. So I think there are two ways, right? So I mean, this kind of proving the equivalence, that's one thing, but I mean, you can also kind of go directly to just refine it to something that maybe is not so fast, but it's enough to actually run a test, right? So I mean, you can execute things inside of ROC itself. So this, for example, the verified CompStart compiler has been executed inside of ROC. It's just quite slow, right? So, but in the first step, you can just kind of write a function inside ROC, which can then be, for example, extracted to a camel, and this is probably enough for running against tests and so on, right? So that can be done in parallel with this proving exercise, which I think is more academic, I guess.
Got it. And talking about the compilation, Alex Hicks is asking, what ballpark performance could you expect when compiling to RISC-V via certicoq or CompCert?
Yeah, so I mean, it's hard to say beforehand. So I would because there are lots of tricks you can do, right? So for example, you can insert. I mean, you could sort of leave a hole for some verified crypto code that you kind of insert. Maybe you prove that in some other setting, right? So I think there are lots of tricks here. As long as you kind of obey the formal verification results, you can optimize in lots of ways. So I would say it's a bit too early to tell exactly what performance we can get.
Got it. And when did you start working on this?
Yeah, I mean, I guess last year, maybe around summertime, something like that. So yeah, well, and I guess the like extraction library. So we build on also lots of other like earlier libraries like this Jasmine and so on, right? So it's more like we looked at the whole ecosystem and kind of try to pull out the parts that people had worked on before that were appropriate.
Kev asks, is it possible to do all of this in Lean?
So probably the definition could be ported. So, so again, I'm trying to use the strengths of this mathcomp library. So unfortunately, I think Lean does not support this what they call canonical structures. So the exact library cannot be ported to Lean due to this, but probably you can do something very, very equivalent to Lean. It's just that there's a kind of ecosystem of how you do proof. So it's basically a style of proof, style of reasoning where you do lots of rewrites. I think that could be emulated in Lean, but it's not as, you would have to do a lot of work on top of Lean, I guess.
Got it. Cool. Thank you so much, Carl. And good to know that the repo is now open source. Maybe it was open source earlier today or yesterday. Yeah, and we have the link in the chat. Cool. Next up, we have our final presentation. And congratulations to the 70 people who made it so far. Ryan who will be talking about ZeroOS. Ryan, the floor is yours. We can't hear you, Ryan. You might be muted.
Not used to using Zoom here. All right. Okay. Hi, I'm Raz, co-founder and CTO of Layer Zero. They were talking about ZeroOS. I'll try to go fast here. So the promise of zkVMs is you can run any code. So you just compile to RISC-V and you're done. The reality is that's not true. There's a massive compatibility gap. I say compatibility does not mean software compatibility. So when you're writing your Rust code, like any of these Rust libraries, they are expecting an OS environment, which that does not exist. So you end up having to fork all of your dependencies and make modifications to them so that they work directly with the RISC-V part. So the current workaround is fork Rust toolchains, patch standard library, and pray that it compiles. But the problem here is that your application, that you are actually forking the Rust code, and that's the standard library part, and it becomes very fragile. And it only works with that version of Rust that you're doing, and it will break on the next one. So this creates this long-term pain where you are trying to keep up with every release of Rust. You lag the upstream security fixes, expanded trusted computing base. As Rust matures, has a mature security pipeline, your fork loses that protection. Every patch that you add increases this audit burden. There's also language hell itself, where you are only most of them are only supporting Rust, which means you miss out if you need, for some reason, C or C++ code. That becomes a pain as well. And then fragmentation. So every zkVM is also doing this process of maintaining their own version of Rust and choosing which versions of Rust upstream fixes to take, and then going through this hell. So we needed a fix at this OS level. So introducing ZeroOS. ZeroOS is the solution that does operates at a different layer, right? It does the syscall trap handler, implements the Linux syscall and traps at the boundary. So what is ZeroOS? It's a universal modular library OS. Acts like a unikernel, so you only compile what you need for what you're using it for. Results here is that you can just take off-the-shelf Rust code in general, like 99% of the crates should just work. You automatically get the upstream fixes from Rust when they make changes to the language. It's language agnostic, so it should just work with Rust, C, C++. Go is on the roadmap for us in the future. And then obviously, if everybody takes on ZeroOS, there's this shared kernel across all zkVMs that have all these benefits. Design principles: it's single core, no interrupts, no preemption. Fast fails, so if there's opcodes that are not, or parts that are not implemented, it'll fail at runtime. It won't
quietly fail there. So you can make adjustments. And then modular, you only include in your crates what you need. Overhead, so it is only 128 instructions per syscall. It is relatively negligible compared to the billions of calls seen in block transitions. So we did a demo, and we have this code available on GitHub. I'll share the links after. We did parallel signature recovery. We implemented ZeroOS in Jolt. We used off-the-shelf Reth recover signers. All clients need to do some multi-threaded version of this. We did that with revm enabled. And here is a snippet of that code. Right off besides the Jolt macros at the top, it is just generic Rust. No extra modifications needed to Jolt itself besides the ZeroOS inclusion. We call recover signers, the actual pulled that library in, called recover signers, and then printed out the results. Here are those results where it ran them. This proof worked and it was valid and did the multi-threaded version. All you had to do for the dependency side is just include thread and std out from the ZeroOS side in your crate, and it just works. That's it. And then you pay for what you use. So it is only those parts of the library from ZeroOS that are included, nothing else, keeping your code and what you compile small and light. And it uses the standard Linux syscall pattern, right? So these are all syscalls that are used in that signature, in that example, and they just work. Language support. So we support Rust, C, C++, and then Go is in the roadmap, ISA, RISC-V. Technically, you should be able to just use, we could build in MIPS or ARM or anything else. It is just, and the idea here is it's a bridge between them. So you could, in the future, have Rust go to the MIP, your Rust code that was working on RISC-V, go to a MIPS-based one later and not have to make many modifications is the dream. So ZeroOS delivers what zkVMs originally promised. No one wants to maintain the two versions in that example. You would have to have two, you'd have to fork Reth and modify the recovery signatures and have to maintain two versions of those. This just works. And then here's the resources for everything. And I'll share the presentation and the links after.
Okay, fantastic. Thank you, Ryan. I guess one question I have is, what is the business use case for implementing this?
So from like our side, we just wanted, we're building zk applications, and we just wanted, we realized that it felt kind of unsafe that we'd have to keep taking on any modification, anything new upstream from the Rust side, that whatever zkVM we chose to work on, that they would have to make a change, and then we'd have to take that new audit risk. And so we wanted to build something that our stuff worked for, and then we would put it in a zkVM that kind of reduces the security risk from our side. So this is open source, MIT Apache licensed. We want this to get implemented everywhere because we want to use it.
Got it. And then in those zk apps that you're working on, have you been using zkVMs other than Jolt?
We've played around with a couple of zkVMs. We talked. We had some conversations with Succinct and others about ZeroOS recently, but we haven't used ZeroOS there. We used it on Jolt so far alone.
Got it. Kev asks, in this model, would all Geth programs rely on the ZeroOS toolchain, i.e. a bug in ZeroOS could mean a bug in correctness?
Yeah, so if everybody implements this, that is the risk. There is obviously we all inherit Linux and other parts of what you're running on that have the risk profile. So the idea is that if everybody's working on this, there's pros and cons. Pros is that we're all working on the same tool chain, and so we're all contributing to making fixes, and we can all get multiple audits on this one thing versus everybody having their own forks and they're getting their own audits and they're all kind of going in fragmented direction. But yes, then there is obviously the trade-off there. That trade-off is that if there's a major bug here, they could introduce a bug on multiple zkVMs. So nothing's free, but we think the risks, the risk is worth the reward here.
Jordi from Zisk asks, does zkOS require MMU in the prover side? I guess he means ZeroOS.
Yeah. Unsure. Isaac here or GX, are you on?
Memory management unit.
Yeah, so I think in the tray, I think it's just like it works well with the current stuff. In the trace, we have an MMU. Like if you look at the Jolt trace, we have that implemented, but we don't have actual implementation of that on the kernel, at least in the case demonstrated.
Okay.
But you should go into the link, the integration guide, look at exactly how the Jolt team integrated ZeroOS into Jolt. We're just facilitating the team to integrate that. Yeah.
Yeah, talking about Jolt, I'm expecting them to make some sort of an announcement and presentation in the next call. You're one of the first teams to kind of make use of them, which is really cool. Kev is asking, what is the base ISA needed from a zkVM in the context of ZeroOS?
I think it's Ryan. I was just answer this. I think it's generic. Like I think it will work on both 32 and 64. But in the case of Jolt, I think we tested with the 64, RISC-V 64, IMA.
IMA. Okay, got it. Any further questions before we wrap up this very, very long call? Cool. If not, just to remind you, we have the very first zkVM breakout on February 11th. And on March 20th, we're going to have a dedicated Poseidon call. Thank you so much, everyone, and see you soon. Have a great day. Bye.